Hello friends, welcome back to my YouTube channel. In this class I am going to discuss some PYQs, that is previous year questions of GATE exam based upon the concept of refrigerator and heat pump. This is in fact the second lecture on the refrigerator and heat pump. In the previous class I solved some numerical PYQs. Before starting, I must say one thing to all of you: please do subscribe to this channel. Of course, like it and share it to your friends. Let's get started. You see, the first question that I am going to discuss is, which was asked in the GATE 2017 mechanical. And the question is like this: a heat pump absorbs 10 kilowatt of heat from outside environment at 250 Kelvin while absorbing 15 kilowatt of work. Obviously, heat pump is a work consuming device, so it consumes this amount of work, 15 kilowatt. It delivers the heat to a room that must be kept warm at 300 Kelvin. So we know that heat pump is usually used in winter days to maintain the temperature of a room at higher level than that of the surrounding. So surrounding temperature is 250 Kelvin. These are the key points. Surrounding temperature is 250 Kelvin, but the room temperature is to be maintained at 300 Kelvin. The coefficient of performance of the heat pump is how much? So we have to calculate the coefficient of performance. You see, the room is to be maintained at 300 Kelvin. Obviously, this is high temperature. TH is equal to, TH stands for high temperature, 300 Kelvin, and the surrounding temperature, that is the TL, is 250 Kelvin. And since the room temperature is higher than the surrounding temperature, obviously heat will flow from the room towards surrounding. So that means this temperature will go down with the passage of time. So to maintain the temperature at this level, we have to continuously supply heat to this. So what is the heat that is transferred from the room to the surrounding? That heat is 10 kilowatt, this much of heat. 10 kilowatt of heat from outside environment. Heat pump absorbs 10 kilowatt of heat. So this is, suppose, your heat pump. This is a counterclockwise device, work consuming device. Suppose this heat is Q dot L and this heat is Q dot H, and this work consumed is W dot, work consumed, power consumed. You see, this amount is given to be 10 kilowatt, 10 kilowatt, and this work or power consumed is given to be 15 kilowatt. This is 15 kilowatt. According to the principle of energy balance, when a system completes a cyclic process, summation of energy that is entering into the system is equal to summation of energy leaving the system during that cyclic process. So by applying that, so this QL dot and W dot are the energy entering into the system, and QH dot is the only energy that is leaving the system. So QH dot is equal to QL dot plus W dot, and this is equal to 10 plus 15, that is 25 kilowatt, 25 kilowatt. So this rate of heat flow to the room to maintain the room temperature of the room at this level is 25 kilowatt. And COP of heat pump, COP of heat pump is desired effect by work input, and here the desired effect is this amount of rate of heat flow is to be continuously done from the low temperature to high temperature. This rate of heat must be supplied to this room so that its temperature will be maintained at 300 Kelvin. If you don't supply this amount of heat, its temperature will go down because the surrounding temperature is 250 and this temperature is 300 Kelvin. So obviously heat will flow from this room to the external environment. So COP of heat pump is desired effect here in this case will be QH dot divided by W dot, and this is equal to 25 kilowatt divided by 15 kilowatt. 25 kilowatt divided by 15 kilowatt, and this is equal to 1.667. So the answer will be 1.667. 1.667. If this was a refrigerator, then its COP would be 0.667 because the COP of heat pump is always greater than the COP of refrigerator by 1, and COP of refrigerator is nothing but the desired effect in case of refrigerator would be Q dot L divided by W dot. COP would have been 10 divided by 15, that is 0.667. So next question is like this. This was asked in the GATE 2017, GATE 2017 XC, GATE 2017 XC. The question is like this. A heat engine receives Q1 kilojoule of heat from a hot reservoir and rejects Q2 kilojoule of heat to a cold reservoir. So Q1 kilojoule of heat engine receives. Heat engine always converts supplied heat, a fraction of heat that it absorbs from high temperature body or source into work output. So it absorbs, suppose, Q1 kilojoule of heat from a hot reservoir, or you can call it source, and rejects Q2 kilojoule of heat to a cold reservoir, or you can say that is sink. Hot reservoir is source and cold reservoir is known as sink. The work delivered by the heat engine is entirely supplied to a heat pump. Work delivered by the heat engine is entirely supplied to a heat pump. That we know that heat pump is a work consuming device. So in this case, whatever work is produced by the heat engine goes to drive the heat pump, which receives Q3 kilojoule of heat from another reservoir and rejects Q4 kilojoule of heat to the same cold reservoir, which receives Q3 kilojoule of heat from another reservoir and rejects Q4 kilojoule of heat to the same cold reservoir. Here that means always refrigerator and heat pump transfer heat from low temperature to high temperature reservoir. So that means in this case Q3 kilojoule of heat is absorbed by this heat pump, and the temperature at which Q3 is absorbed will definitely be less than the temperature at which it rejects Q4 kilojoule of heat. That is the same cold reservoir. Q4 kilojoule is rejected to the same cold reservoir, that is your TL. That same TL that is applicable for heat engine. Suppose the figure is like this. Suppose this is the high temperature reservoir for heat engine. Here Q1 heat is absorbed by the heat engine, and Q2 heat is rejected to the low temperature reservoir. This is low temperature reservoir, and here the whatever work, suppose work produced is W. This goes on to drive the heat pump, and suppose this Q3 heat is absorbed from another low temperature reservoir, that is suppose Tm, and this is again the heat transferred to the same reservoir to which heat engine rejects it. This reservoir is common to both heat engine and heat pump. Q4 is rejected to the low temperature reservoir, that is written in the question. Q4 kilojoule of heat to the same cold reservoir. This is the cold reservoir TL, and obviously here the temperature is like this. TH is greater than TL is greater than Tm. Tm will obviously be less than TL, since refrigerator and heat pump transfer heat from low temperature to high temperature. So this Tm will be obviously be less than TL. So this is the relation between these three temperatures. So we have to calculate, and efficiency of the heat engine is given to be 0.4. Efficiency of heat engine is given to the 0.4, and COP of heat pump is 4.0. We have to calculate the value of Q2 plus Q4 divided by Q1 up to 1 decimal place. You see, efficiency of this heat engine is given to be 0.4. Efficiency of heat engine is nothing but here W upon Q1, that is given to be 0.4, and the COP of this heat pump is nothing but desired effect by work input. This W, whatever work is produced by the heat engine, is the work input to the heat pump. So COP of this heat pump is nothing but Q4 by W. Q4 by W. From this, you see W by Q1 is 0.4 and Q4 by W is given to be 4.0. On multiplying this, W by Q1 multiplied by Q4 by W is equal to 4 into 0.4, that is 1.6. But we have to calculate Q2 by Q2 plus Q4 divided by Q1. So Q4 by Q1 we have just found out. This is on multiplying, this is what? This is Q, W cancels out. So Q4 by Q1 has come out to be 1.6. Q4 by Q1. So if we are able to find out Q2 by Q1, then we will add it to the Q4 by Q1 to find out this term. Q2 plus Q4 whole divided by Q1 is Q2 by Q1 plus Q4 by Q1. Q4 by Q1 we have already calculated and it is 1.6. So we have to calculate Q2 by Q1. Q2 by Q1, efficiency of this heat engine can be expressed also like this: 1 minus Q2 by Q1. 1 minus heat rejected by heat supplied. That we have already discussed. Efficiency of any heat engine can be written as 1 minus Q2 divided by Q1. 1 minus heat rejected by heat supplied. This is given to be 0.4. So from which Q2 by Q1 comes out to be 0.6. Q2 by Q1 comes out to be 0.6. So Q2 by Q1 0.6 and Q4 by Q1 1.6. So on adding this, Q2 plus Q4 by Q1 is nothing but Q2 by Q1 plus Q2 by Q1 plus Q4 by Q1, that is Q2 by Q1 is 0.6 and Q4 by Q1 is 1.6. So 0.6 plus 1.6, this is 2.2. So this is answer is 2.2. So next question is question number 3. Question number 3. So a refrigerator is used to maintain certain space at 10 degree Celsius. A refrigerator is used to maintain a certain space at 10 degrees Celsius, and it pumps 18,000 kilojoule per hour of heat from space to atmosphere at 30 degrees Celsius. So refrigerator, the main function of refrigerator is to maintain the temperature of a space at a level lower than the temperature of atmosphere. So atmospheric temperature in this case is 30 degrees Celsius, but the space at which the temperature is to be maintained is the temperature of the space is to be maintained at 10 degrees Celsius, obviously less than surrounding. So if the power input to the refrigerator is 2 kilowatt, obviously power input होता है refrigerator and heat pump में work input होता है. The ratio of COP of this refrigerator to that of a Carnot refrigerator up to 2 decimal places is how much? So GATE 2017 EXE में पूछा गया था ये सवाल. So let's solve this. So question is like this. Suppose the higher temperature, obviously refrigerator and heat pump are devices which transfer heat from low temperature to high temperature. So here high temperature reservoir is 30 degrees Celsius, that is here the high temperature body is here the atmosphere. So 273 plus 30, that is 303 Kelvin, and low temperature body is 10 degrees Celsius, that is 283 Kelvin. This is the space, the temperature of which is to be maintained at 10 degrees Celsius or 283 Kelvin, where the surrounding is at 30 degrees Celsius, or in terms of Kelvin, that is 303 Kelvin, and refrigerator has to operate. So power input here is 2 kilowatt. This is 2 kilowatt. So power input is 2 kilowatt. Next is the ratio of COP, and it pumps this much of heat from space to atmosphere. So you know here the temperature of atmosphere is at 30 degrees Celsius and this is at 10 degrees Celsius, low temperature. So obviously heat will continuously flow from surrounding to this space. Obviously heat will flow continuously from surrounding to this space. So how to maintain, the temperature will increase. So how to maintain at this level? We can't afford to have a situation in which the temperature of this space will increase. That we can't afford to. So for that we have to continuously extract whatever amount of heat enters into this space, that has to be continuously extracted by your refrigerator. Suppose this is Q dot L. Q dot L is given to be 18,000 kilojoule per hour. 18,000 kilojoule per hour. And what has been asked to find out is the ratio of COP of this refrigerator to that of a Carnot refrigerator. You see, suppose this is Q dot H. So first we will find out the COP of this actual refrigerator, and then we will find out the COP of Carnot refrigerator that operates between these two temperature levels. Then we will go on to find out the ratio. So COP of actual refrigerator is, desired effect by work input, that is Q dot L divided by W dot. This is refrigerator, desired effect is this Q dot L. This is equal to 18,000 kilojoule per hour. We have to convert this into kilowatt. So that is 18,000 divided by 3600 kilowatt divided by 2 kilowatt. This is equal to 5 kilowatt divided by 2 kilowatt. This is equal to 2.5. This is the actual refrigerator, COP of actual refrigerator. COP of Carnot refrigerator operating between these two temperature limits TH and TL is, which we have already discussed, is TL divided by TH minus TL, that is, here TL is 283 Kelvin, 283 Kelvin divided by TH is 303, TH minus TL, that is 303 minus 283 Kelvin, and this is equal to 14.15. 14.15. So if you, but the question is to find out the ratio between these two, COP of actual refrigerator, COP of this refrigerator to that of a Carnot refrigerator up to 2 decimal places. So actual refrigerator, COP of actual refrigerator is 2.5 and the COP of Carnot refrigerator is 14.15. Obviously the COP of Carnot refrigerator and Carnot heat pump between two given temperature limits is always the highest. So COP ratio will be, that ratio will be 2.5 divided by 14.15, that is equal to 0.1766, and if you round up this to 2 decimal places, this will be 0.18. So answer will be 0.18. 0.18. So next question is question number 4, that was asked in the GATE 2016 mechanical engineering, and the question is the COP of a Carnot heat pump operating between 6 degrees Celsius and 37 degrees Celsius is how much? This question is very easy one, and you see, so this is the higher temperature is, higher temperature TH is, higher temperature TH is here 37 degrees Celsius. On adding 273 to this becomes 310 Kelvin, the higher temperature, and low temperature is 6 degrees Celsius. So on adding 273 to this, TL is 279 Kelvin. 279 Kelvin. So obviously the COP of Carnot heat pump we have to calculate. So this is, suppose, Q dot L, this is W dot, this is Q dot H, but we have to calculate the COP of Carnot heat pump. So Carnot heat pump, COP of Carnot heat pump will be, Carnot heat pump will be TH divided by TH minus TL, and this is equal to 310 Kelvin divided by 310 minus 279 Kelvin, and this is equal to 310 Kelvin divided by 31 Kelvin. 31 Kelvin. This is equal to 10. So the answer will be 10. The COP of Carnot heat pump will be 10. And if you are to calculate the COP of refrigerator, Carnot refrigerator, of course, it would have been 9, because the COP of heat pump is always greater than the COP of refrigerator by 1. So next question is question number 5, that was asked in GATE 2016. GATE 2016 mechanical engineering. The question is like this: the heat removal rate from a refrigerated space and the power input to the compressor are 7.2 kilowatt and 1.8 kilowatt. Whatever power is consumed by the refrigerator, that is mainly the power required to drive the compressor. In fact, in case of a vapor compression refrigeration system, it is the electricity consumed, and in other systems, different kind of energy is transferred. So here the Q dot L is given, and this is the heat removal rate, and this is the W dot work required input. So the COP of the refrigerator you are required to find out. Very straightforward question this is. You see, suppose this is the high temperature reservoir or body, and this is suppose low temperature body, and the refrigerator is always used to transfer heat from low temperature to high temperature body with the help of some external work. Suppose this is Q dot L, this is Q dot H, this is W dot. You see, the heat removal rate from a refrigerated space, Q dot L, is given. This is 7.2 kilowatt, 7.2 kilowatt, and work input is given to be 1.8 kilowatt. This W dot is 1.8 kilowatt. Obviously, this Q dot H will be 7.2 plus 1.8, that is 9 kilowatt, but we have nothing to do with this. So now COP we will calculate. COP of refrigerator will be desired effect by work input, that is Q dot L divided by W dot in. This is equal to 7.2 kilowatt divided by 1.8 kilowatt. This is 4. COP of refrigerator is 4, and if it would have been a heat pump, the answer would have been 5. So answer is 4. So next question is question number 6. A household refrigerator operates under steady state condition between an evaporator temperature of 263 Kelvin and a condenser temperature of 323 Kelvin. In case of a vapor compression, obviously when evaporator and condenser is given, means it is a VCRS or vapor compression refrigeration system, and evaporator temperature is always the TL, and the condenser temperature, evaporator temperature is always the lower temperature, and condenser temperature is high temperature, which is 323 Kelvin. It is given. The heat load to the refrigerator is 3 kilowatt. Heat load means this is the cooling load, or this is the heat removal rate that is given to Q dot L, 3 kilowatt. The actual COP of the refrigerator is half of that of a Carnot refrigerator operating between the same condenser and evaporator temperatures. So actual COP is in fact half of that of maximum refrigerator COP, that is the COP of Carnot refrigerator operating between the same condenser and evaporator temperatures. Then you are required to find out the power required in kilowatt to run the refrigerator is how much. And the question was asked in GATE 2016 XC. So you see, the higher temperature is given to be 323 Kelvin. This is condenser temperature, and evaporator temperature is low temperature. Lower temperature is given to be TL is 263 Kelvin. 263 Kelvin. So suppose this is the refrigerator. This is Q dot L. This is given to be 3 kilowatt. The heat load to the refrigerator is 3 kilowatt. The heat load to the refrigerator is 3 kilowatt. So Q dot L is 3 kilowatt. And suppose this is W dot, power input. Obviously, these are power consuming devices, refrigerator and heat pump. This heat that is going to this high temperature body is Q dot H, suppose. So you see, whatever has been given in the question is COP of actual reservoir, actual refrigerator divided by, this is given in the question, COP of actual refrigerator divided by COP of Carnot refrigerator is 1 by 2. This line you see. The actual COP of the refrigerator is half of that of Carnot refrigerator operating between the same condenser and evaporator temperatures. So we are to find out the power required in kilowatt. W dot we are to find out. So that means COP of actual refrigerator divided by, you see, COP of Carnot refrigerator is nothing but TL divided by TH minus TL. TL here is 263 divided by 323 minus 263 is equal to 1 by 2. So COP of actual refrigerator, COP of actual refrigerator, you see, COP of actual refrigerator, COP of actual refrigerator divided by, this ratio is, you see, 263 by 60 is equal to 1 by 2. So now we will calculate COP of actual refrigerator from this. COP of actual refrigerator is equal to 263 divided by 60 multiplied by 1 by 2. Multiplied by 1 by 2. This is equal to 263 divided by 120, and this is equal to 2.191. 2.191. This is the COP of actual refrigerator. But you see, COP of actual refrigerator is nothing but Q dot L divided by W dot. You know, one important thing is you should not be confused that the COP of refrigerator and heat pump is always can always be expressed in terms of temperatures. And whenever you write the formula that COP of refrigerator here will be TL divided by TH minus TL, and COP of heat pump will be TH divided by TH minus TL. That formula is applicable only for Carnot refrigerators, COP, only to find out the COP of Carnot refrigerator as well as Carnot heat pump. But for any refrigerator, be it reversible or irreversible, we can express the COP of refrigerator and heat pump in terms of heat and work interactions. So COP for any refrigerator, this is in fact the COP of this refrigerator will be, sorry, COP of actual refrigerator has come out to be 2.191, and COP of this refrigerator is, you see, QL dot divided by W dot. Desired effect is Q dot L divided by W dot. Q dot L, that Q dot L divided by W dot has come out to be 2.191, and Q dot L is nothing but 3 kilowatt, that is heating load given in the question, that is also, divided by W dot is equal to 2.1. सो यहाँ से हम निकल के लाते हैं W डॉट इज इक्वल टू W डॉट इन एक्चुअली इनपुट, वर्क इनपुट इज इक्वल टू 3 डिवाइडेड बाय 2.191, that is equal to 1.369 kilowatt. 1.369 369 kilowatt. So answer will be, the power required in kilowatt to run the refrigerator will be 1.369. 1.369 in terms of kilowatt. This is the power required. And had this been a Carnot refrigerator, the power required would have been less. In fact, in work consuming devices, if they act in reversible cycle, then the work input would be least. And in case of power producing devices, if they act reversibly, then the work produced is the maximum ones. So that's all. Thanks for watching.